Alright, in this video I'm going to look at an object moving in a vertical circle. It's going to have a mass of 0.5 kilograms, and we're going to look at the range of speed that are going to allow it to go in the circle at a uniform speed. So we have a 0.5 kilogram object, 0.5, tied to a string. The string is 0.5 meters long. It's going to swing around in a circle, a vertical circle. The string can sustain a force, a maximum tensile force of 10 newtons. So what are the range of speeds that we could use to swing that 0.5 kilogram object without breaking the string, but while making sure we're going fast enough to go through the top of the loop without falling? So the minimum speed is going to be set at the top of the loop. At that point, the object needs to be accelerating at least as fast as acceleration due to gravity, or else the object will fall out of the circle. So the minimum speed is going to occur at the very top here, and at the very top, since there is a force of gravity pulling it back into a circle and we want to go as slow as possible, we're actually going to set the force of tension in the string to 0. So here we are. We have an unavoidable force of gravity, assuming we're swinging this thing on the surface of the Earth. And if I put any force of tension here at all, then what that's going to do is pull the object back along into the circle even faster. So since we're interested in the minimum speed or the lowest speed possible, we're going to set this force of tension to 0. Any force of tension makes it go faster, so we'll just get rid of it completely. With that in hand then, that the force of gravity acting on this object is mg, 0.5 kilograms times negative 9.8 newtons per kilogram, or negative 4.9 newtons. That is the only force, we're ignoring wind resistance and stuff like that, acting on this 0.5 kilogram object, so we can also say it's the net force. And with our net force, we can use our formula for circular rotation, or acceleration in uniform circular motion, mv squared over r, and that way we can come up with the v. So we have 4.9 newtons here, our mass of 0.5 kilograms. We don't know our velocity, so we'll just put it in as v squared. And I'm just interested in the magnitude of this speed, so I'm ignoring directions here. And the radius, if the string was 0.5 meters long, then that's going to be the radius of our circular motion. So with that in hand, these 2.5s effectively cancel each other out. We just have to square root that 4.9. And we get a minimum speed of 2.2 meters per second. The maximum speed is going to occur at the bottom, because at the bottom the force of gravity, as well as the inertia of the object, is trying to pull it out of the circle. So the force of tension has to be very large to pull that object back up into the circle. We know our maximum force of tension that will let it go as fast as possible is 10 newtons. So we're going to assume at this point in the circle that our force of tension is 10 newtons. Our object is still 0.5 kilograms big, and so the force of gravity on it is the same as the calculation I did over here, negative 4.9 newtons. What that leaves me with then is a net force in the upward direction of 5.1 newtons. So for my maximum speed, I am going to say that my net force is again equal to my equation for the centripetal force, or the force required to keep something moving in a circle with uniform velocity, just r, not r squared. So I'll put my 5.1 newtons here, mass of 0.5, radius of 0.5, just like last time, v squared. These two cancel each other out, And so to get V, kilograms and meters, so that makes all the units work. So to get V, all I have to really do is square root 5.1. Which works out to 2.3 meters per second. So those two turned out to be very close to each other. So the minimum speed was 2.2 and the max was 2.3. So what we can see in this question is we have a very narrow range of possible speeds that could be used to swing this object in a vertical circle. Chances are we won't be able to maintain that speed exactly, so this question is a little bit unrealistic. You'd probably break the string before you're able to maintain a uniform circular motion. We looked at the top. We set the force of tension to 0 and had the force of gravity being the only thing maintaining the circular motion at the top. That created as small force as possible and led us to as small a velocity as possible. Then we looked at the bottom, recognizing that the force of tension has to overcome the 4.9 newtons. We know that this is the first point where the string will break if it's going too fast, so this represents our maximum speed. Maximum speed. This represents our maximum speed at this location. And so here we recognize that the force of tension has to overcome the force of gravity to find our net force, and worked out to the max speed that we should be able to see.